we realize that humans realize this, okay, that if you have a circle, come on, get back in there. There we go. If you have a circle and you take the radius and you swing that radius along the arc, that this angle is always the same regardless of the radius. And so that's a very unique angle. It's very special. And we should give it some sort of name. Why don't we call that 1 radian? This angle right here, we're going to call it 1 radian. Because it's, regardless of how I do this, we're always going to get back to this same angle, right? So that is it. We call this 1 radian. 1 radian. Now, how do I say that? Like, how do I write that down in words? Like, if I ask you what a degree is, you're going to say it's 1/360th of a rotation, right? That's what a degree is. You take a full rotation, you cut it in 360 degrees. If I ask you to define a radian, you're going to say, oh, it's this thing that Jason and Robert did up on the board where they like measured. I mean, that. So how do we actually define a radian? It's ugly. Let me see what the book does. I don't even know if they're even going to go for it. They don't even go for it. Okay, they don't try to define it in a way that they just go right to telling you that there's a relationship between radians and degrees. But this is what it is. All right. So let me try and define it in words. 1 radian is the angle formed when the terminal side of an angle lies, this is going to still sound bad, okay, but at least I'm trying to put it down on paper, lies at the end point, I'll just put end, of the arc of length equal to radius. Okay, I know that sounds terrible, but let's just try and understand what it is, what I'm saying here. 1 radian is the angle that's formed when the terminal side of the angle, right, lies at the end, that's this point, lies at the end of the arc that has a length that is equal to the radius. Make sense? That's 1 radian. I won't quiz you on that, but that's what it is. You want to know what a radian is? That's basically the idea. Now, the big question becomes, we know that there are 360 degrees in a full rotation. How many radians does it take to create a full rotation? And this is where it all goes out the window and people go crazy. Because you want it to be a nice number, like 360 degrees, you want it to be a nice number. Like, oh, it's 5 radians and we've gone all the way around. Unfortunately, it's not the case because the radian was not created for convenience. The radian was created because of this weird sort of like anomaly that we found that always happened. And so we had no control over how many of them were going to be in a full rotation. But it turns out that there are some. Let's see how many there are. How are we doing on time? So I'm going to go back here to our Cartesian plane. This is about 1 radian right here. Okay, I'm just eyeballing this, okay? That's 1 radian. 1 radian. 2 radians is about here. Okay, so that's 2 of them. I'm just going to put 2 rads. And I think I'll use a different color so that you don't confuse it with the X and Y axis.
Try again.
An error has occurred. Try again later. I don't know what's going on. I need to shut that thing up. Okay, this and this, that's 2 radians. 3 radians is almost 180 degrees, not quite. Unfortunately, it's not. 4 radians, 5 radians, 6 radians. This is 6, 5, 4. And unfortunately, 7 radians is past a full rotation. So it's not, the numbers don't work out nice. Do y'all see what I'm saying? Like, it just kind of sucks, but it's the way it is. But there is something that is quite remarkable. This 180 degrees is a little bit more than 3 radians, right? That's what this is saying. But that means it's got to be like 3 point something radians, right? Yeah? It's actually 3.1415, that real important number. It's pi radians. Pi is approximately, you've seen pi, I know. Pi is approximately 3.1415, right? And that's exactly how many radians there are in a half rotation. So if you wanted to know what this exact 180 degrees is, what's the equivalency? If this is 180 degrees, that is equivalent to pi radians. Understand that pi radians means 3.1415 radians. Understand that? And this one over here, 2 pi, which is, I just gave it away, 360 degrees is a little bit more than 6 radians, and it's exactly twice as much as this, right? So if this is pi, then twice, you got to go around again, halfway around. So this would be 360 degrees, which is the same as 2 pi radians. Make sense? Here's a way I guess I could make the analogy. I think you understand, I hope you understand the difference between degrees and radians, but let me do it this way. Let's say that we have this stick, and I want to find a way of measuring it, so I decide to cut it into 360 smaller pieces, right? That's what we did for degrees. For radians, what we did is we said, hey, you see that stick? I don't care about the stick. I have this thing right here. This length of this phone. I love this thing. This thing is awesome. I love just that length. It's just awesome. And so I'm going to see how many I can fit into here. And I wind up having some hanging off the end. I'm like, oh, well, but I love this. I want to use this as my measurement. So I'm going to have like 1, 2, 3, 4. Maybe I'm going to have like 8.265 of them. See the difference? I didn't start with this and cut it into pieces. I started with this and fit it in here. That's the difference. Okay. Now, when you write things in radians, like pi, you do not have to write rad. You don't have to write it. You don't have to write 2 pi radians. You can leave radians off, and it is understood that it is radians. If you're going to write something in degrees, you must put the degree symbol, otherwise it's assumed to be radians. Now with that in mind, let's see if we can go revisit our common angles. Let's look at our common angles. Start with this one. What is that in radians? 0?
Or
what?
2 pi.
2 pi, or 4 pi, or 6 pi. So right, to get it here, to get back to there, I would either not rotate. I go around once, which would be 2 pi. I go around twice, which would be 4 pi. Understand this? 6 pi, 8 pi. So how can I do that using that cool notation? 2 pi k, 2 pi k, 2 pi k. If k is 0, where are you? 0. If k is 1, 2 pi. K is 2, 4 pi. Understand that? 2 pi k. Are you sure you don't have questions on that? Let's try this one. Ooh. Start here, end here. So I want us to end there. All right? This is my initial size, end there. So what is that angle in radians? Pi, right? So get yourself there. So to get yourself there, you just put pi, right? Now you're there. Now get yourself back there. Plus a full rotation, but in radians, what's a full rotation? 2 pi. So I say plus 2 pi k. Is that, no? Yes? Okay.
I have a question. I should have asked this earlier. Why do we have to stop on the terminal side?
Why do we have to stop?
Yeah, like why do we always have to come back to the terminal side?
What I'm trying to get you to see is this angle right here is pi. Do you agree?
Yeah.
But that's not the only angle it could be. It could also be negative pi. But that's not the only two. You could go, how about you go all the way around once, that's 2 pi, right? And then keep going and stop here. Wouldn't that be 3 pi? Yes? So this is pi, 2 pi, that'd be 3 pi, I'd be there also, right? Now I could have gone backwards. I could have gone all the way around, that's 2 pi. Negative 2 pi, sorry. Negative 4 pi. Stop, that's negative 5 pi, right? Well, I could sit here all day. I could sit here for the rest of my life listing out every single possibility. This does that for me. Because if k is 0, we've got pi. If k is negative 1, what would you have? If k is negative 1, what would you have? Wouldn't that would make that a negative? And pi minus 2 pi is negative pi? And that would put you here, right? So I've got that one covered. And I could just keep on doing different values of k to generate all the different angles. Does that help answer?
Yeah.
You sure? Okay. What about this one? Start here, and I want you to be able to end there. So yeah, pi is the whole way around, so that would be half of it. Half of pi. You can write that pi over 2. That's the way we'll write that. Half of pi, we write pi over 2. Now, if I wanted all the answers, what would you do? Plus 2 pi k. Add that full rotation to get yourself back there. That would represent all those angles, all of them.
An error has occurred.
All right. I think you're getting the idea. I hope you are. Let's move on. I want to change gears a little bit. I want to look at I want to look at this idea of the area of a sector. So this is a pretty significant change of gears. area of a sector and arc length of a sector. Okay, first thing we need to know is what is a sector, all right? So if I take a circle, which we've studied, we've talked about circles a little bit already. If I take a circle and start off with the, let's say, an angle in here. So let's say we have this as our initial side, and then we have some terminal side over here. And then we imagine this thing in here. That is a sector. Slice of pizza, right? That's a slice of pizza. There are two things that would be worth knowing, and that would be, do we have a formula for the area of that sector, and do we have a formula for the length, arc length of the sector? So let me show you what the difference is. The arc length right here, we call this S. That's arc length, okay? It's just the measurement of that outside piece, all right? Then, the area itself is all this shaded stuff in here. That's the area of a sector. You see the difference between the two? Arc length versus area. Yes? No? Maybe so? Yes? Okay. Well, fortunately for us, there are two formulas that we're just going to provide to you. If you wanted to know where these came from, you can actually prove both of these formulas in a calculus class. I know in my Cal 2 I proved both of these, but it's way into the class. So you'll see the proof if you're like one of those people, well, I don't believe it, I need to see it. This is one of those things, just please take it on faith, stand by, take Cal 2, you can see the proof, all right? So here we go. What do you want first, arc length or area? Really doesn't matter which one we do first. We'll do arc length? Okay, so arc length. S is equal to R theta. That's it. It's such an elegant, perfect little formula. I forgot to put R on here, but I was hoping you understood that this was the radius of the circle. Isn't that a nice formula? If you want to know the measurement of this little crust of your pizza, then all you have to do is take your radius and multiply it times what? Your angle, right? That's what this says. To find the measurement of the crust, the length of the crust of your pizza, take your radius and multiply it times the angle. Now, when we say angle, theta, oh, I didn't label theta, darn it. I assumed you knew theta was that angle. When I say theta, though, couldn't that be in degrees or radians? Well, in this formula, it has to be in radians. So when you write this down, must be in radians. If you don't do that, you will have big trouble. You'll get the wrong answer. Let's do an example. An example of this. Let's say you have this little slice of pizza. Let's say that this is 7 inches. I'll put little inches there. Don't confuse that with minutes, seconds from angles. I'm not talking about that. 7 inches. And let's say that this angle in here is pi over 6. So remember, isn't pi is a half rotation, isn't it? Pi is halfway around. So this is 1/6 of that. So there's your pizza. How long is S? How long is this S? What is it? So let's get our formula. Let's plug in and get it, right? So S would be what? R 7 times pi over 6, which is just 7 times pi over 6, which is something, right? Now, if we wanted to know it as a decimal, we would get our calculator out and we would do 7 pi and then divide that by 6. Who has that approximately for me? 3.66519. Good enough. About 3.665. What? Yes?
There would show us degrees instead of the pi over 6. We would have to convert it.
We'll have to convert, which we haven't talked about the conversion, but yes, we would have to convert it. We will do that. I don't know if we'll have time today. We're going to spend more time in this section next class because it's just so important that you get all these little things down. So that means S would be 3.665 what? What is S measuring? It's the length of this, right? Which would be inches. So that crust would be about 3.6 inches or so. Y'all with me? This is kind of interesting. I think it's interesting. Look at that formula over there, S equals R theta. If I divide both sides by R, I get that, don't I? The right side of that equation is radians, yes? It's how many radians you have. How could I get this to be 1 radian? What would I need to happen here for this to be 1 radian? No, just look. No, forget. Just look at this. Look at this right here. If I need this to be 1 radian, what do these have to be? In order to make them the same, right? To be 1, they would have to be the same, which means R would have to be equal to S, wouldn't it? 1 radian is when R equals S. Go back to your picture. If R and S are the same, that's 1 radian. This is what we were doing up here on the board with the cable. If R is equal to S, that's 1 radian. But this formula can actually generalize to this. Now, I just wanted to point out, I think that's kind of cool. How about this? What is circumference of a circle? Yeah, so here we go. We've got a circle, radius r. Now, a lot of you have probably memorized this formula. Maybe you haven't, it's been a long time. What is the circumference of a circle? It's the measurement all the way around, right? Does anyone remember the formula? Circumference equals 2 pi r. That's the formula that somebody gives you at some point and says, hey, the circumference is 2 pi r, right? All right, let's go back to this. If I want to use this formula instead of that, then what I'm trying to measure is this arc length, right? The arc length was this edge right here of the pizza. But I want the edge of my pizza to go all the way around. I want the whole pizza. Which means if that's S, this is R, what's theta? What's all the way around? I heard it, but you can't use degrees. It's 2 pi, isn't it? It's 2 pi. So using this formula, S equals R theta, you would have R, which is R, and then what's theta? 2 pi. And what do you get? 2 pi R. So it's actually, this circumference formula is actually a specific example of this formula. So this formula is more powerful because it can be used for any angle. This is specifically when you want to go all the way around. Do y'all see that connection? Kind of cool. All right. Let's talk about converting. I think we know. I'm going to hold off on the area, sector area. You won't need it in this section, so I'm going to hold off on that for just a moment. Let's talk about conversion from degrees to radians and radians to degrees. Converting degrees to radians and the other way. Okay, so both ways. How do we do it? Well, we're going to use what are called conversion factors. And the conversion factors are just very straightforward formulas. We know, first of all, that 180 degrees is equivalent to pi radians, right? Yes? That's understood? I mean, I told you to believe that it was exactly pi, but that's kind of our starting point. This is the basis for all of our conversions, is using this. Now, what I'm going to do, from this, I'm going to create two conversion factors. The first conversion factor says this: 1 equals 180 over pi, and the other conversion factor says 1 equals pi over 180. I really want you to understand what I just did there. I took this assumed equation that we agree is true, and I created these two things. How did I create this one? What did I do to go from here to here? I divided both sides by pi, right? If I divide 180 by pi, I get 180 over pi. If I divide pi by pi, that's hard to say. If I divide pi by pi, I get 1, okay? So that comes from dividing both sides by pi. This one, both sides by 180. So these two are the only conversion factors you need in order to convert degrees to radians or radians to degrees. And here's how we'll do it. Let's say we have 60 degrees, and I would like to convert that to radians, right? I am allowed to take anything in the world and multiply it by 1, right? If you multiply anything by 1, you get back itself. It doesn't change the problem, right? So when I'm sitting here, I'm thinking, okay, I'm going to multiply this by 1, but I get to choose which one I want to use. Do I want to use this one or this one? Well, I'm trying to get rid of degrees, right? Yes? So if I'm trying to get rid of degrees, I want the degrees in the denominator over here so that they'll cancel out. That makes sense? So what I'm going to do is essentially multiply this by pi over 180. And then this is just like basic fraction multiplication. You go straight across the top, straight across the bottom. You get 60 degrees pi over 180 degrees. And you get a common factor there, don't you? Like 60 goes into both of those. And the important thing is that the degrees are going to cancel. So what are you left with? Pi on top, what's still on the bottom? 3. Pi over 3. And that's where you leave it. And this is in radians, and it's understood it's in radians. I don't have to write radians next to it. Make sense? Okay, how about this? If I want to do 5 pi over 3, and I want to convert that to degrees. So this is in radians. How do you know it's in radians? Because there's a pi and there's no degree symbol in there. So you know that's in radians. Let's go to degrees. So again, I get to choose from these two. I would like to use the one that has pi in the bottom because it'll cancel the pi that I have, right? So I go ahead and multiply this by 180 and divide by pi. And then the pi's cancel. And you get, I think, 300 degrees. So you can do the math here, however you want to simplify that, but 300 degrees. So I know that some of you have learned in the past, like converting, that you you do these two operations, like either do this one or this one. I know that some of you have learned that. The reason I did it like this, I want you to understand that really conversion factors always just come from some basic understanding of the connection between the two things. From that, you can create your own conversion factors. So if you know this is true, then you don't even have to memorize these. You can almost like create them yourself. That makes sense. And you can do that for anything. You can do that for if you have 1 foot equals 12 inches, right? Then you could create two fractions. 1 foot over 12 inches equals 1, and then the other one could be 12 inches over 1 foot equals 1. And then now you can always convert from inches to feet or feet to inches. You just use either this one or this one depending on what you want to cancel. This is the way all conversion factors work. Y'all tired? Y'all ready to go? We have 10 minutes still. Oh, sign-in sheet. I'm not going to forget this time. I forgot to pass this out last week. And weren't we off Tuesday? Right? We had the holiday, the winter holiday. So I want you to sign in. There's going to be your name, and then there's going to be a column here. It'll be Tuesday, Thursday, and this Tuesday. So I want you to initial 3 times. And if you weren't here, then don't say you were here. Integrity. Yeah. All right. Let me see what else I want to say while we're kind of packing up. We still have more to do. I didn't quite finish this. So I would say if you go to do your homework out of 7-1, realize that you're probably going to start running into problems, issues about, I don't know, number 53 is where you're going to start to have issues. Also, just a little bit about the way the lectures work and the homework works. I'm up here, I'm trying to get you to understand ideas, but I really want a lot of learning to take place while you're doing the homework. And that's why I provide you the solutions. Like there's going to be a problem in the homework where you're asked to convert an angle that's given to you in degrees, minutes, and seconds over to just degrees. And I never even showed you how to do something like that. So if you were to sit down and do your homework, you'd be like, what the heck? So I expect that those homework solution videos will be there as a tool to help guide you through that. Now, most of the time, things that I will ask you on a test will be something I'm going to do in here. The homework kind of encompasses more. The test will be focused more on what you see in here. Okay, any questions? Yes.
What about our take-home quiz?
Take home.
Yeah, last class we gave us that problem and told us
The completing square one, and then see how you do on it. I thought y'all turned them in.
of this circle.
Yeah, I thought y'all turned them in. No?
So we turned it in her class.
Yeah, turn them in. Yeah, sorry. Yeah, if I give y'all a take-home problem to work out, just bring it in next class, slap it on the desk. That was that one where I said if you tried and you couldn't get it. Did anyone get it? Do you feel good about it? Okay. McKinsey and Keller?
yeah.
Yes, okay. Make sure you sign in before you leave. We're cutting out a little early, but I think you'll be okay with that, right? Just today? Just this one time?